coming to you from Jezero crater on the surface of Mars. This is Mr. C.
Happy Thursday to you, 7th graders. See, I've got a picture to show you right away I want you to have a look at. So, mystery photo. What is this? What is it? I think it's one of them there instruments that measures earthquakes. That's what it is. This is a seismograph. Can you see the graph paper? Seismic means shake. Seismic waves are earthquake waves, shake waves. And here's how this works. It goes into the ground. A part of it is in the ground, actually slightly underground, sticking into the crust. And if there's an earthquake and the ground shakes, then the part that's stuck in the ground shakes, and then eventually this needle shakes that has ink coming out of it, and it writes on the graph paper, and you can get an idea how strong an earthquake was. If you see several places where the lines spread out further on the graph paper, those were registered earthquakes. This is a seismograph. Will I include it in tomorrow's test? Yeah, seismograph. Seismograph. So it will indeed be included. And if you look here, you can see how to spell it. Well, maybe. Down below, can you see that? Seismograph. This one actually was used at a volcano site. Seismograph. And you already know this. If there's a chance that a volcano is going to erupt, or at least if it's active, then magma will move under the volcano. So magma comes up under the volcano and it'll shake the volcano a little bit. And seismographs that are positioned around the volcanic mountain will register that earthquake and let the volcanologist know, well, that particular volcano is active and who knows what's going to happen. They might even make a prediction that it could erupt at some point in recent history. So anyway, seismograph. There it is. So now you know on tomorrow's test you can use a note card. In fact, I highly recommend it. In fact, if you don't do well and you don't use a note card, you know what I've already said, you'll have to retake. Yeah, you'll have to retake it. So I don't want that. So I want you to do well. So use a note card and fill it up with all the information that we've gone over and that I'm going to go over in a little bit. And that's included in homework notes in Wednesday's homework notes for you guys. Here's the latest United States Geological Survey earthquake map. Ring of Fire, very active. Active earthquake right under Kilauea in Hawaii. What does that mean? Magma's moving underneath. On the southern end of the mid-Atlantic ridge, down at the bottom of the Atlantic Ocean in the middle, so mid-Atlantic ridge. Look down there in the bottom. There's one down there. Well, it just now turned, yeah, you see it, it's orange, but you can see it. So things going on at the southern end of the mid-Atlantic ridge, so I wanted you to see that. Then I wanted you to see these pictures of the 1964 9.2 moment magnitude scale earthquake, the second largest earthquake ever recorded, and the greatest moment magnitude ever recorded in the United States. Alaska, 1964. The ground shook so hard it just collapsed. It fell down about 10, 12 feet. Look at that. The ground shook so hard it just fell, collapsed. Got another picture for you. The same earthquake, 1964 Alaskan earthquake. Look at that. Here the ground shook so hard the boulders and houses and trees just fell over and got shook up like a mixing bowl. These are about the most violent evidences of an earthquake that I could show you. I mean, there are others too. Tsunamis pretty violent, aren't they? Yeah. So anyway, there was a tsunami in connection with this Alaskan earthquake, and it covered up one whole town. I think the tsunami wave was the highest I've ever heard of. I think it was 100 feet. It was a massive tsunami wave. Remember, you get tsunamis with subduction zone earthquakes that occur on the coast, and that's usually where you get the really big ones. So where an ocean plate goes down underneath or above, either one, a land plate. So it's a kind of convergence, where they come together and either go up to form mountains or drop down underneath and form volcanoes or do this. Sometimes the one that's the ocean one slips up like this. This is water, right? So it's under the ocean, and one of them slips up like this. Well, it throws water toward the land in a big tsunami wave, like you saw in the Japanese earthquake that occurred. So anyway, I wanted you to see that. And then I wanted you to see this. I know you had seen this, but I'd like you to see it again. Watch these buildings shaking. Imagine you were in that high rise. Look at the building. Look at it shake. That's your high rise that's moving, and the one across the way too. That would be scary. And then check this out again. You can actually hear the building creaking as it's going back and forth. I can hear it really well here because the speaker's right near me. So as it's moving, it's creaking. Now in Japan and in California, where there are big earthquakes, not a subduction zone in California, it's one of those translational ones, side-to-side movement on the San Andreas Fault. But anyway, so in those places, the governments make sure that they make the buildings more earthquake safe. Now, you can't make a building 100% earthquake proof. You can make it a lot safer. And you read about that, and that was your homework. So you're going to want to pass that in, name, date, period, on what they do to buildings, where they use the cross pieces and they use dampers underneath between the building and the floor to absorb some of the shock. They have shock absorbers. Some of them have rollers, so they'll roll a little bit. So they give up some of the earthquake energy. So if the building didn't give up some of it, it would do like this. It would bend and bend and bend, and then snap. And I mean, they could fall over, and they have. Like there was a Mexico City earthquake that was 8 plus maybe, or 8.0 on the moment magnitude scale when? I think it was in the 1980s. And some of the buildings, the high-rise buildings, just fell over because they didn't have very good earthquake building laws. So they weren't built that safe, and big earthquake, and they fell over. Were there a lot of people that went to heaven? Yeah, it was terrible. It's really terrible. So anyway, you know our good news. Our good news is that because we live on a stable part of the North American plate, we don't have big earthquakes. And we're not on the coast, so obviously we don't get tsunamis. So when I ask you that tomorrow, why don't we get big earthquakes here in Arizona? Because we're not near a plate boundary where there's a big crack between two plates. That's over in California on the San Andreas Fault. The San Andreas is the big crack between the Pacific plate, which is moving one way, and the North American plate moving the other way. But here's what they do. I didn't finish this for you yesterday, so let's see if I can do it. Here is my metric ruler. So 50 centimeters equals the Pacific plate, and this is the North American plate. So they bend and they bend and they bend and they bend and they bend, and then they break. So this is a simple model, but it works. So the stress builds and builds as the plates move, and then they give. That would be a smaller earthquake. Sometimes, though, they lock up for years, decades, sometimes hundreds of years, and the more they lock up, then the bigger the earthquake is. So stress, 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 break, snaps. So anyway, I thought that might be kind of a good way to show you how it works. And then I already showed you the biggest earthquakes ever. The biggest one was the one in Chile in 1960. It was a 9.5. Then the 9.2 in Alaska. And number 4 was a 9.1 in Japan in 2011 that had the tsunami that I showed you, and where the buildings were swaying. That was tied for third greatest moment magnitude scale ever measured. I heard once in my geology class that if there were a 10 earthquake anywhere, it would be felt everywhere on the earth. A 10. I mean, it would be felt everywhere. Obviously, right where it happened, it would really be felt in a great way. This will be on the test, of course. What do you call the place underground? Here's the surface of the crust where the rock breaks down here. What do you call that? Remember the focus. It's got a U in it, and it's underground. That's the focus of the earthquake, where the rock breaks underground. Where the earthquake waves happen right up above it, right above, that is the epicenter. That's where the waves are centered. So focus, epicenter. Focus, epicenter. Focus, epicenter. Focus, epicenter. Right there. Okay? And those would be great questions to ask as well. And I will ask those. So in a little while, I have a video to show you on the San Andreas Fault. I think you'll find it interesting, but that's not for now. So I want to really quick, I think I have them under here. I want to really quick show you the minerals that I'm going to ask you, and my good buddy that I showed you yesterday. These are the ones you've got to know. Okay, you ready? So here they are. So I would recommend whipping out your mineral chart. And I'd mark these up or highlight them. These are the ones I want you to know. This one, of course, volcanic, it's igneous. What is it? Lots of little holes. Pumice. So you're putting these down. So pumice, big chunk of sandstone, sand grains, sandstone. So pumice, sandstone. Are you marking these? Purple quartz, Amethyst, right? Okay. Regular quartz, same shape of the crystals, same shape, this white quartz. And then the major rock found in the crust under the ocean. It's volcanic, igneous, what is it? Basalt. Basalt is at the bottom of the ocean. Basalt is at the bottom. I'm trying to give you some brain glue. And then this is found in continental crust. We have big chunks of it on campus, I keep telling you. What is it? Say it out loud. Granite. Granite, continental crust. Basalt on the bottom of the ocean, oceanic crust. And then this one, this pair, I'm going very quickly. So this one's the mud rock, shale, and it gets heated and squeezed, metamorphic, into slate. Shale to slate. Shale, heated and squeezed, into slate. That pair, I want you to know. Another igneous, volcanic glass. It's obsidian. Volcanic glass. Obsidian. There'll be a matching on these. Okay. And I added this one, fool's gold. A lot of it was found in Arizona, California. Turned out not to be gold, loaded with iron, so it's iron pyrite. Looks like gold. Fools ya, doesn't it? Iron pyrite, fool's gold. Okay, just four more. This Arizona one that's got copper in it. Copper is found in chrysocolla with a C. This is going to be a matching, so should be easy peasy. Chrysocolla has copper in it, and you can see some of the copper? Maybe. Okay. Down to 3. This is coal formed by the Great Flood, one kind of coal, soft coal, anthracite. Kind of coal. Are you marking these? This one has a magnet on it. It's loaded with iron. It's rusted. It's got rust marks on it. Magnetite. And then this one is the writing mineral. It's the lead in your pencils. In your pencils. So it's graphite from the word grapho, meaning to write. Graphite. Makes sense. You write with pencil lead or graphite. You write with it. It's a lead in pencil, so you write with it. Graphite. Okay. How many were there? All right. I added 3. Actually, I added 2 because there's the pair, shale to slate. So I added 2. I added chrysocolla and I added graphite. No, I added iron pyrite. So anyway, I'm matching on those. So study those a bit. Okay. And then let me check on the time, how we're doing. Okay. Doing pretty well. So I just have just a few minutes to help you. So with the test. Okay. I wanted to remind you just about the science activities in the back of the room. There's 4 in A, 4 in B, and 4 in the C cubby and or cave, and 4 in the D. And you were to put those in your journal a long time ago, many, many months ago. I'm going to check those, and I'm going to call for them on May 19th. That's a Wednesday. So you want to make sure you have all of those done, and many of you do, so double check it. And Mr. Phillip and myself, from time to time, each week are going to give you a few minutes to work on those. If you end up needing time to finish, you can always finish in advisory. They're going to be worth about 2 points each. So that's 16 times 2, 32 points, huh? It's a lot of points. So you want to make sure you have those when I check your journals out. I am going to call for them on the 19th. So, and don't forget, on the 14th, SSRs are due. Okay? And then really quick, just a few other, because I want to save time for your video I'm going to show you on the San Andreas Fault. You'll have to write Psalm 19:1 tomorrow, and you can't write it on your note card. The heavens declare the glory of God, the sky above proclaims his handiwork. You have to know what a constellation is. I told you this yesterday. A star pattern that of some familiar object we see on Earth. And then a couple of things you can do for Earth Day. Conserve water and pick up trash in your world, wherever it may be. That could be school, could be home, neighborhood, with parents' permission, of course. Proteins, I'm going to ask you a couple of questions about proteins. Proteins are made of amino acids, and the reason they're so complex is you have thousands of them in your body. And they're long chains of the 20 amino acids that have a totally different pattern, and that's why this will be a bonus point. The chance for just one 150 amino acid forming randomly or by chance, 1 over 10 to the 164th. So that's 1 over the fraction, the denominator of 1 with 164 zeros behind it. No way it could happen. No way, Jose, no way. I'm going to ask you something about the Mars helicopter. What's its job? To fly, not to crash, and to take photos of Mars. So I'll ask you those. I'm going to ask you Laura's major point last week. You can do, are you writing it down? You could write it on a note card right now if you had a note card. You can do anything that you practice and practice and practice. You can do it better. And you'll get pretty good at it. Maybe not the best, but you'll get really good at it if you practice. I'm going to ask you something about the supermoon. Why does it look bigger, and why is it brighter a couple of times a year? Because of the elliptical orbit. Look, flattened circle, elliptical. I want you to do this 3 times with me. Count of 3. Get your circle up there. Then we're going to go 1, 2, 3, ellipse. Do it with me. 1, 2, 3, ellipse. 1, 2, 3, ellipse. A flattened circle last time. 1, 2, 3, ellipse or elliptical. So when it's at this point of where my index fingers are and where my thumbs are, it's closer to the Earth. So it looks bigger. It isn't bigger, but it just looks bigger. So if I show you this chunk of the anthracite right here, it doesn't look all that big. But if it gets closer, does it look bigger now? Yeah, same thing with the moon. So it's far away, and then at those 2 places, when there's a supermoon, it moves closer. Okay? Anything else? All the earthquake stuff I'm going to ask you. Okay, I'm going to ask you the kinds of waves. The first wave, P waves, they're primary waves. They get there first. First school, primary school. Primary waves get there first. They all shake the ground. And then S for secondary waves. And then surface waves. They all shake the ground in different ways. Some go side to side. Some go up and down. Some do this. They compress and decompress. Push in, push out. Okay? So I'm going to ask you for those. I'm going to ask you for the way the plates move. Sideways, they converge and diverge, seafloor spreading. Subduction. Probably ask you for an example. Okay? Of course, I'm going to ask focus and epicenter. So I'm going to ask those. So the minerals, I'm going to ask those. So all of this you can put on a note card. So anyway, I've got a brief video for you on the San Andreas Fault. It's a side-to-side movement plate movement. So you will see it. Also, remember, I'm going to ask you seismograph, the instrument that has the drum that rotates with graph paper on it. And if the ground shakes, it leaves a mark on the graph paper. So, anywho, it's about time to show that video, and then if there's any time left, perhaps Mr. Phillip will answer any last-minute questions, or maybe he'll do that now first, and then there might even be time for a little bit of review time. So test tomorrow, note card, triple R bid anyway. Just because you have the note card, you've got to complete it in, limited amount of time. Okay, take it away, Mr. Phillip. Thank you, sir.